Hi guys, Mr. Ford here. I'm going to go through a couple of the PhET simulations done by the University of Colorado. You could see the website at the top if you forget or want to kind of play with them yourself. So we're starting electricity, so hopefully you watch the two Edpuzzle videos. They could be a little bit confusing. They are a little bit involved with the math. We'll get into that eventually in the packet. Just starting off, we're going to start with electrostatics, which is basically a static electricity that you experience, mostly during the winter when it's really cold and dry. And it's just because you have more charge on one object than another. And when you see that spark, sometimes when you touch a metal object after rubbing your feet on the carpet, usually with socks, you're equaling that charge as electrons are moving. So if you remember from chemistry, electrons are on the outer part of an atom. They're the lightest of all three particles, so they're the ones that are going to interact. They're easier to pull off and also move because of the less mass. So here we have the app. It's called John Travoltage. You can see that that's John Travolta if you know who he is. If not, shame on you. So this is what he's going to do. He's going to pull some electrons off the carpet by moving his foot, and they get spread out through his body. Yeah, we can move his arm. So if we take as many as we can, we are increasing the overall negative charge in him. It doesn't mean that he doesn't have positive charges in his body. He just has more negative. So he's overall negative. And he's going to bring his hand closer to the metal door. And what you're actually seeing in that spark is the electrons moving through the air or to the ground or something else that had more charges to neutral it out. So essentially he's negative and the door handle is all positive or mostly positive. So you're going to have that equal of charge, that attraction of opposite charges. Something to note a little bit, though, if you bring his hand a little bit closer, let's see, you don't need that much of a buildup of charge to have that charge dissipate. So moving his hand further, you do need more of a difference of charge. Kind of works like magnetism. The stronger the magnet, the further apart they can be to have an effect on the forces or movement. This might be a little bit too far. I think we're maxed out there, so if we bring his hand a little bit closer, there's the difference. So hopefully you understood that. Feel free to go to that website and play around with that. Now we're going to look at balloons. We're looking at the same thing. In the video, Mr. P does this. He takes the balloon, he rubs it on his hair. In this case, we have a sweater. So we pull all of the electrons off, leaving it mostly positive. The balloon is mostly negative now. We can kind of show that with just changing the bottom. So if I reset them. So in the beginning, everything is neutral, but we are taking off. We're taking this off from friction because we're physically rubbing it off. And then they're attracted. Of course, opposites attract. But take a look at the wall. As we pull this mostly negative balloon towards the wall, what happens to the negative charges in the wall? They move away. But when we move the balloon back, they move back as well. And this is because we're not rubbing the electrons off of the wall. So it depends upon the material, whether it's holding onto its electrons tightly or loosely, whether you could take the electrons off. So we looked at charging objects through friction only by pulling off the electrons. Right now, we're separating that charge. So if you look in the wall, that little chunk of wall, I'll show this to you later in a drawing. I can't draw on this. That the portion of the wall is positive, that's near the surface of the wall, and then farther into the wall, it's all negative. This is known as charging by induction because we're not transferring the charge, but we're just merely separating it. So when you separate the charges by bringing another charged object near it, that's charging by induction, which is sometimes temporary. We can also look at Coulomb's law. This was one of the first videos you looked at. This was the one that really looked like the law of universal gravitation. Very similar app or simulation as the one for universal gravitation within PhET. So if we just increase the charge, let's make them both negative. So the saying is opposites attract, same charges. If they're both negative, they repel and push away. So the bigger the charge, the more that electrostatic force is, just like gravity. If we move them further or closer, the further away they are from each other, the less of the force, and the closer, the greater. And we could see this by that equation that we'll look at in a second if you don't remember it from the video. But take a notice, if we have opposite, so charge 1 or Q1 is positive, which is the red one, and then charge 2 or Q2 or the blue one is negative, it's an attraction force. So that's the main difference between, well, one of the main differences between looking at universal gravitation and electrostatic forces. Universal gravitation was always attractive, meaning the forces were towards each other. But for electrostatic forces, or Coulomb's law, they can be attractive or repulsive. It depends on the sign of the charges. So opposites attract, same charge repel. So negative, negative will repel, and positive, positive will repel. So let's take a look at some things. So basically, the takeaway from those videos in this one, you should note that we're talking about electrostatics. That's essentially static electricity. There's 3 ways that you can charge an object. We looked at friction, basically pulling off of those extra electrons from one object to another. If we separate charges, and there's multiple ways to do that, we looked at one. That's called charging by induction. And then conduction is when things are in contact. So you kind of look at the John Travoltage one, where he rubbed his feet on the carpet, he was charged, and then he transferred that charge to the doorknob by simply touching it or getting close enough to where that charge could jump through the air. Coulomb's law, this was the universal gravitation and electrostatic force. Equations are very similar. G was a constant, K is a constant in this case, which we'll get to. It's not the same as a spring constant, though. Just note that. It's a little bit different. Again, for the electrostatic forces, they are attractive or repulsive. Gravitational was only attractive. So we'll go through a little bit more tomorrow in a video along with the packet that is in Schoology. No need to print it out. We can go through just from that PDF, and you could write stuff on a piece of paper. You can do it electronically if you know how to use that technology, or you can print it out if you have a printer and want to use that paper and ink. So until tomorrow, see you guys later.